If there is a place in the universe where everything can only come out and nothing can ever go in, what would you call it? We're used to thinking about black holes, cosmic mouths that swallow light, matter, even time itself. Once something crosses that invisible boundary, it never returns. Black holes feel final, absolute, almost mythic. But physics, quietly and without drama, offers us an opposite idea, a white hole, not a monster that consumes, but a one-way fountain of space-time, a region where nothing can enter and everything inside must escape. Light, matter, energy, even causality, stretched thin, seems to flow outward. This isn't science fiction, and it isn't a lecture. Think of this as a journey, one that moves slowly, from familiar ideas to strange ones, from images you can picture to concepts that feel just out of reach, step by step, question by question, not to overwhelm you, but to let your intuition adjust, the way your eyes adjust to darkness. If you stay, you'll discover why white holes appear naturally in the mathematics of Einstein's universe. Why, despite that, they are almost impossible to observe, and why this idea, quiet, abstract, and elusive, touches something deeply human. Because at its core, this mystery isn't just about exotic objects in space. It's about time itself, why it moves forward, why it never seems to turn back. So let us stay very close to where we just were. Not rushing anywhere, just standing quietly beside one strange idea and letting it unfold at its own pace. Imagine a long hotel corridor. Soft carpet, dim yellow lights, a row of identical doors, all closed, all quiet. At the far end, a single door carries a glowing red sign, Exit. You know exactly what that means. You can walk through from this hallway to whatever lies beyond. But you cannot come back in through that door. That rule is not written into physics. It is written into building codes and habits. Now let the wallpaper fade. Let the ceiling vanish. Let the corridor dissolve until only emptiness remains. And then, underneath that emptiness, the invisible structure of space-time. No walls, no lamps. Just the thing that lets events line up, that lets you say before and after. In that structure, imagine a region that behaves like that exit door. Not because people decided it, but because the geometry insists on it. Everything inside is allowed to go out. Nothing outside is allowed to go in. That is the feeling of a white hole. Its sibling feels more familiar by now. A black hole is the other kind of one-way door. A place in space-time where everything is allowed to go in and nothing is allowed to escape. You can fall toward it. You can cross its boundary. But once you cross, every path that your future can take leads deeper in. No path leads back out. So in the simplest language, a black hole is a region where escape is forbidden. A white hole, in the same simple language, is a region where entry is forbidden. Same family, two opposite rules, two orientations of a one-way door. When people first hear the phrase white hole, imagination tends to sprint ahead. Some picture a kind of anti-black hole made of antimatter. Others see a teleport gate, spitting out spacecraft on the other side of the galaxy. Others think of something like a science fiction respawn point, a place where whatever falls into a black hole emerges again. The real idea is quieter than that, and, in a way, stranger. A white hole is not made of antimatter. It is not a fantasy portal. It is not simply a black hole that has decided to spit things out instead of swallowing them. It appears when we take Einstein's description of gravity seriously and refuse to stop at the first answer that feels comfortable. It appears when we let the mathematics run all the way to the edge of what is allowed. On the 25th of November 1915, Albert Einstein stood before the Prussian Academy of Sciences and presented the field equations of general relativity. In a compact set of symbols, they say that matter and energy tell spacetime how to curve, and curved spacetime tells matter and light how to move. There is no mention of black holes in that talk, no mention of white holes, no diagrams of wormholes or fountains. Still, everything that comes later rests on that day. Once those equations exist, the universe is no longer just a stage where forces act. The stage itself can bend and twist. It can form traps, funnels, horizons, and one-way doors. For a long time, even black holes were treated with suspicion. The equations seemed to allow them, but many physicists thought nature would quietly avoid them. Real stars have pressure. Real matter is messy. Perhaps, people hoped, there was always some physical effect that would stop a collapse before the point of no return. Black holes, in that view, were like the dragons drawn at the far edges of old maps. Interesting, but probably not real. Then the sky replied. On the 10th of April 2019, the Event Horizon Telescope collaboration released an image that circled the world. Not a crisp photograph in the everyday sense, but a reconstruction from radio waves gathered by telescopes scattered across the Earth and combined as if they were one planet-sized instrument. Against a glowing ring of hot gas sits a dark interior, the shadow of the black hole at the center of the galaxy. Messier 87, often called M87 star. That dark patch is not empty space. It is the imprint of an event horizon, a one-way surface beyond which light itself cannot return. We are not guessing here. The ring's size and shape match exactly what general relativity predicts for a black hole of that mass. Something that lived in paper and equations for decades has taken on a visible outline. Years earlier, the universe had already found another way to speak. On the 14th of September 2015, a little before 10 in the morning, Coordinated Universal Time, two large instruments in the United States recorded the same tiny pattern. A rising and falling stretch in the distances between mirrors, much smaller than the width of a proton. This was the first detection by LIGO of gravitational waves from a black hole merger, an event now labeled with the compact code GW150914. Two black holes, each born from the collapse of a massive star, had spiraled together far away, lost energy as gravitational waves, and finally merged into a single, heavier black hole. The brief, final moments of that dance sent ripples through spacetime itself, and those ripples reached Earth. For the first time, we were not just calculating black holes, we were listening to them. So, the idea that black holes are just math no longer survives. We have watched stars near the center of our own galaxy whip around an unseen mass. We have seen the shadow of M87 star. We have recorded the space-time shudder of distant mergers. The abyss is part of our observed universe, and that is exactly what makes the white hole so unsettling. Because the white hole does not come from a different theory. It is not a new set of equations bolted on top of what we know. It appears in the very same solution that gives us a black hole, if we insist on extending that solution as far as it will consistently go, both into the future and into the past. If a black hole is an abyss mouth, a region where everything can fall in and never return, then a white hole is the opposite mouth. Not swallowing, but erupting. A region where matter and light stream outward, but nothing from the outside universe can ever cross inward past its horizon. A one-way door locked in the opposite direction. You can picture a volcano, frozen into an odd rule. Lava flows outward, ash falls outward, gas rushes outward. Now imagine that none of the surrounding air, none of the rocks, none of the falling debris is ever allowed to cross inward through the same surface. The eruption continues, but the rest of the world is not permitted to touch the source. In the black hole story, the horizon forms because something in the past collapses. A star runs out of fuel, its core implodes, pressure loses its battle against gravity, and space-time pinches off. Once the horizon appears, everything inside is doomed to move forward toward the singularity. The strange region has a history we can picture. A cloud of matter that used to be spread out, then shrank. In the white hole story, the direction flips. The horizon is already there in the distant past. Its interior is filled with matter and radiation arranged in an extremely precise way. All of it set up so that, as time passes, it will stream outward through the horizon and then disperse. Instead of a messy collapse, you have a carefully tuned explosion that was waiting to happen. From a human perspective, that feels backwards. We are used to coffee cooling, not heating itself. We are used to eggs breaking, not shells reassembling in midair. We are used to clouds slowly spreading, not gathering themselves spontaneously into sharp shapes. A white hole, taken literally, looks like the second kind of story, an improbable past leading to a mundane future. This is where thermodynamics and the arrow of time quietly enter the room. The equations of general relativity, by themselves, do not care about past or future. If a certain pattern of geometry and matter is allowed as a solution, then the time-reversed pattern is also allowed. For every black hole that forms and persists into the future, a time-reversed twin exists in the space of possibilities, erupting from a singularity in the past and fading away. Most physicists suspect that the universe never chose those reversed versions, at least not in any obvious way. Not because they are forbidden by the laws, but because they require an almost impossibly special starting point. It is like writing down every way the molecules in your room could be arranged, and noticing that there is one precise configuration in which all the air happens to huddle into one corner. The laws allow it. Reality almost never does. Still, the symmetry is there. For every acceptable black hole solution that stretches into the future, there is a mirror image that stretches into the past. For every region where all paths lead inward, there is a region where all paths lead outward. For every abyss mouth, a mouth of eruption. You do not see that when you look up on a calm night. The constellations do not reverse themselves. The Milky Way does not flow backward across the sky. On human timescales, the universe looks steady and slow. But on a page filled with symbols, or on a computer quietly solving Einstein's equations, you can trace curves of light that never cross inward, only outward, through a horizon that cannot be entered. You can draw a singularity that lives in the past, not the future. Think of it as a hidden layer beneath the familiar one. Not a hidden layer of extra objects, but a layer of possible histories the universe could, in principle, have followed. Histories where some regions behave like white holes, not because they break the rules, but because they use the rules in that unfamiliar direction. You do not need to decide tonight whether such regions exist anywhere beyond the page. It is enough, for now, to let the idea sit beside you. Gravity, in its most honest form, allows two kinds of one-way door. One that accepts everything and never lets it out. One that never accepts anything at all. In the corridor of spacetime, both kinds of exit sign can be written. Whether the universe chose to light both of them is a separate question. Outside, the sky does not move, but inside the mathematics, something is flowing backward through diagrams and symbols, like a film played in reverse. Every frame allowed by the same patient equations. To watch how that backward flow first appeared, we have to step away from the stars for a moment and return to a human scene. A physicist at the front lines of a world war, sending Einstein a letter that carried the first exact solution to the new field equations. A solution that would later reveal, hiding inside it, both the familiar black hole and the ghostly outline of a white one in its distant past. The scene is almost there already. A man at the edge of one kind of chaos, quietly uncovering another, stranger kind, that lives far beyond shells and mud and smoke. Picture Europe in winter during World War I. Trenches carved into frozen ground, artillery in the distance, a sky the color of old paper. Somewhere on the Eastern Front, an officer in the German army spends his scarce quiet hours not sleeping, but calculating. His name is Karl Schwarzschild. He is not in a quiet office in Berlin. He is close enough to war to hear it. Yet in those conditions, with illness quietly growing inside him, he does something most of us would associate with calm libraries and blackboards. He takes Einstein's new field equations, barely weeks old, and looks for a clean, exact solution. Not an approximation, not a rough sketch, a precise description of how spacetime curves around a single spherical mass. On the 22nd of December 1915, he writes a letter to Einstein. In it, he says, almost casually, that he has found such a solution. A closed-form answer. An exact way to describe the gravitational field of a spherically symmetric body. It is as if, from a battlefield, someone has sent back not news of movement or loss, but a perfectly drawn map of how the universe bends. Einstein receives the letter in Berlin. He recognizes immediately that this is something rare. On the 13th of January 1916, he presents Schwarzschild's work to the Prussian Academy of Sciences. In the space of a short talk, an abstract equation gains its first clear, concrete child. The mathematics of curved spacetime now has a specific example. A shape. That shape, today, bears Schwarzschild's name. At first glance, it sounds harmless. The Schwarzschild solution describes spacetime outside a spherically symmetric mass that does not rotate and does not change with time. You can imagine a perfect, non-spinning star or planet. The solution says, if you put such a mass in otherwise empty space, here is exactly how distances and time intervals will be distorted around it. Nothing in that description screams danger. It feels almost gentle. A round mass. Symmetry in every direction. Stillness in time. But folded inside this clean solution, invisible at first, there is a boundary. In the coordinates Schwarzschild used, something odd happens when you move closer to the center. Far away, the equations behave well. Closer in, still fine. But at a certain radius, the equations, written in that particular way, seem to break. Quantities that were finite suddenly blow up. The metric coefficients misbehave. It would be easy to shrug and say, this is just a bad choice of coordinates, like using latitude and longitude at the poles. In fact, part of what is happening is exactly that. A coordinate singularity, not necessarily a real physical one. Yet, the location where this breakdown happens is not arbitrary. It sits at a specific radius, proportional to the mass. And when people looked more deeply, they realized that this radius marks something important. It is what we now call an event horizon. The phrase sounds dramatic, but the concept is quiet. An event horizon is not a wall. It is not a physical shell you could touch. It is not made of any particular matter. Instead, it is a boundary in spacetime that separates events that can communicate with the outside universe from events that can never send a signal out. You can imagine hovering above this boundary in a powerful spaceship, engines roaring, holding a fixed distance from the mass. As long as you remain outside the horizon, there is always a way, at least in principle, to turn around, fire your engines, and escape to safety. If you cross inward, the nature of your future changes. No matter how you fire your rockets, no matter how clever your maneuver, every possible path forward leads deeper in. None lead back out. That is what makes the horizon a boundary of fate rather than a wall. Nothing dramatic needs to happen when you cross it. The local conditions can be almost ordinary, but globally, in terms of where your world line can go, the change is absolute. An image helps here. Picture a wide river that gradually becomes faster and steeper as it approaches a cliff, far upstream. You can swim, turn around, paddle to shore. As you drift closer to the edge, the current strengthens. There is a line on the water, not marked by a buoy, not visible from above, where the current becomes so strong that no swimmer, however powerful, can make it back upstream. Cross that line, and every possible motion carries you toward the waterfall. Outside that invisible line, escape is possible. Inside, it is not. The river itself is continuous. The water does not suddenly change color, but the structure of possible futures for anything in the water changes at that edge. In the Schwarzschild solution, the event horizon plays the role of that line. Outside, the future still offers many options. Inside, every option ends at the singularity, a place, or more accurately, a region, in the mathematical description. where curvature becomes extreme and our current theory stops being trustworthy. Of course, in the years right after Schwarzschild's letter, this story was not yet clear. Physicists were still learning how to read the geometry. And the theory itself, though elegant, was untested. Then the sky provided a chance. On the 29th of May, 1919, a total solar eclipse cut a dark path across the Earth. Expedition teams went to islands and coastal towns along that path, including the island of Principe in the Gulf of Guinea and the town of Sobral in Brazil. Their goal was simple in concept and delicate in execution. Photograph stars near the eclipsed sun and compare their apparent positions to where they appear in the night sky when the sun is elsewhere. If general relativity is correct, light passing near the sun should be bent by the curvature of spacetime around it. The apparent positions of those stars should shift by a very specific amount. It is a tiny effect, invisible to the naked eye, swallowed by daylight under normal conditions. Only during an eclipse, with careful equipment, could it be measured. The observations were difficult. The plates were not perfect, but the deflection they suggested lined up within error bars with Einstein's prediction, not with the older Newtonian estimate. When the results were announced later that year in London, newspapers around the world carried headlines saying that Newton had been overthrown. The language was exaggerated, but the message was simple. Gravity is not just a force in space. It is a change in the structure of space and time themselves. From then on, general relativity was no longer only a beautiful theory on paper. It had been tested in the field, in the light of distant stars grazing the Sunday. The map that Schwarzschild had drawn around a spherical mass rested on firmer ground. As people learned to navigate that map, they began to see more in it than Schwarzschild himself had time to explore. The apparent singularity at the horizon could be removed by choosing better coordinates. New ways of charting the same spacetime made it clear that the horizon is a smooth surface, not a place where the geometry truly tears. More importantly, when the solution is extended as far as it can consistently go, not just outside the mass, not just for a finite stretch of time, but in all directions allowed by the equations, something unexpected appears. The full, maximally extended Schwarzschild spacetime does not just contain one region outside a black hole and the black hole interior. It also contains a mirror region in the past. In the waterfall picture, we have been following leaves as they drift toward the edge and fall. The extended solution, however, tells us that there is another side to this story. A region where the water seems to come from somewhere else, rushing outward over a different edge that cannot be approached from outside. In the language of general relativity, that mirror region behaves like a white hole. In that region, every possible path points outward, away from a past singularity. Nothing from the outside can cross inward through its horizon. Everything inside is destined to exit. It is the time reverse of the black hole region, where one has a future singularity that swallows, the other has a past singularity that erupts. You do not get this white hole region because someone decided to add it. It is not bolted on by hand as an extra idea. It appears because the mathematics has a kind of memory. The equations of general relativity respect time reversal in a deep way. If a particular pattern of curvature and matter is allowed, then the pattern with time reversed is also allowed. When you insist on treating the Schwarzschild solution fully and fairly, honoring that symmetry, the white hole arrives as part of the package. Another metaphor can help anchor this. Think again of our river and waterfall. Now imagine a mountain spring instead. Water emerges from a hidden source in the rock and flows outward in all directions. No stream outside that spring can ever push water back into the hidden source. The flow is one way. Just as the waterfall has a critical line beyond which everything is dragged in, the spring has a kind of inverted boundary from which everything moves out. The black hole is the waterfall. The event horizon is the edge. The white hole, in this picture, is the mountain spring. Its horizon is the place from which everything flows outward, and nothing from the surrounding streams can penetrate back to the origin. Of course, Rivers and springs are made of water. Black holes and white holes are made of spacetime geometry itself. They obey equations rather than plumbing, but the structure is similar enough to give intuition. One region pulls in, the other pushes out. One has a horizon that traps, the other has a horizon that repels. In our actual universe, we know ways to form something like the waterfall. A massive star can collapse, gas can fall inward. Over cosmic time, the abyss mouth can appear. For the spring, the story is less clear. You would need the universe to begin in a state so carefully arranged that a white hole is already there in the deep past, ready to pour out its contents. That is part of why most physicists treat white holes with caution, as elegant features of the extended solution, but not necessarily as objects that ever formed in the messy history of our cosmos. Still, their presence in the mathematics is important. It tells us that general relativity, taken strictly, refuses to forget about the other direction of time. Even if reality prefers one side of the coin, the theory quietly preserves the outline of the other. So from a letter written during a war, carried through a lecture in Berlin, tested under the shadow of an eclipsed sun, we arrive at a space-time that contains more than we expected. A simple, symmetric mass, described exactly, hides a one-way boundary that divides possible futures. And when that description is unfolded to its full extent, it reveals not only an inward-falling region, but also an outward-flowing mirror in the past. We have been looking at this structure mostly from the outside, as if standing safely on the riverbank, mapping currents and edges. To understand why crossing the horizon changes everything, we will have to follow the geometry inward, past the line where hovering becomes impossible, and into a domain where what we usually call space and what we usually call time begin to trade places, quietly switching roles, like cards turned over in a slow, patient trick. There is a strange kind of helplessness that has nothing to do with courage or fear. It is what happens when the shape of the world around you quietly removes your options. We are used to thinking of going forward as a choice. You can slow down, sit, turn around, walk away. If you stand on a hillside or on a street corner, nothing in the geometry of Earth forces you toward a particular direction in time. You age. Yes, the clock moves, but you can still walk north, south, stay where you are. Around a black hole, that freedom has limits. Far from the horizon, space still behaves in a way that feels familiar. You can orbit in a circle. You can fire your engines and climb away. You can, at least in principle, choose not to approach the dark region at all. Closer in, the current strengthens. At some point, there is a critical surface, the event horizon. Outside it, there is still a future in which you escape. Inside it, that part of the future simply ceases to exist. Not because anyone forbids it, but because the geometry no longer contains those paths. The difference is subtle and absolute. Outside the horizon, there is always some trajectory that leads back outward, even if it demands impossible fuel. Inside, every possible trajectory, every tilt of the rocket, every attempt to turn, ends at the singularity. It is as if you were in a city where, once you cross a certain invisible ring, every road, every alley, every side street bends inexorably toward the center. The city map contains no route that misses the middle. Except here, the center is not a place you could choose to visit early and then leave. It sits in your future, in the same way tomorrow sits in your future. It is not an address. It is a fate. This is one of the oddest lessons of general relativity. Inside a black hole, the direction we usually call inward behaves mathematically like the direction we usually call forward in time. Once you cross the horizon, falling inward is no longer something you are doing. It is something that is happening to you, the way aging happens. You are not simply moving, you are being carried. You can imagine dropping a clock and a small lamp as you fall. The hands of the clock tick on. The lamp keeps shining. Locally, nothing special announces that the horizon has passed beneath you. You feel weightless, as you would in any free fall. But globally, from the perspective of space-time itself, there has been a switch. What you might have called a direction in space has become something more like the direction of your life. This is not a trick of language. In the equations, the coordinate that measures distance inward plays the role of time inside the horizon. The surfaces that were like moments outside become like places. It is not just that you are trapped, it is that the structure of what trapped means has changed. For a while, black holes were imagined as perfectly silent prisons. Whatever crossed the horizon would be lost forever, its information sealed behind the boundary. Nothing could come back out. Outside, observers would only ever see the frozen, red-shifted ghost of the infalling matter, never the fate inside. Then, once again, the theory surprised its authors. On the 1st of March 1974, a short paper by Stephen Hawking appeared in the journal Nature with a title that sounded almost playful. Black hole explosions? Inside that paper was a sharp claim. When you combine general relativity with quantum field theory, a black hole is not entirely black. It emits radiation, with a precise spectrum, as if it had a temperature. The effect is unimaginably tiny for astrophysical black holes. The radiation is weak, the temperature low. But the principle was a kind of table flip. Black holes, long treated as purely absorbing objects, became thermodynamic systems. They could radiate. Over enormous timescales, they could, in theory, lose mass and shrink. A year later, in 1975, Hawking's more detailed work on this phenomenon, particle creation by black holes, appeared in Communications in Mathematical Physics. The picture sharpened. The radiation is not magic. It arises from quantum fields near the horizon, from the way vacuum fluctuations are stretched and separated by gravity. One part of a virtual pair falls in, the other escapes. From far away, the black hole looks as though it is emitting particles. This did not make black holes safe. It did not soften the inevitability inside the horizon, but it added a new layer to the story of time. Black holes now had entropy, a measure of the number of microscopic states compatible with their macroscopic appearance. They had temperature. They fit into the same thermodynamic framework that governs steam engines and melting ice. That connection matters for white holes. Because once you know that black holes behave like hot objects, you can no longer think of time reversal as a purely poetic operation. If you contemplate reversing the process, you are no longer just flipping a sketch. You are asking, what would it mean to have an object that absorbs nothing, emits everything, and somehow runs the entropy movie backward? The tension becomes sharper when you remember that black holes are not just theoretical in the sky. They have left fingerprints in our instruments. On the 11th of February 2016, the LIGO and Virgo collaborations announced that they had detected gravitational waves from a black hole merger. The same September signal whose date is encoded in its name, GW150914. The story they told was not of static prisons, but of dynamical, violent events. Two black holes in spiraling, circling faster and faster, then plunging together, the horizon surfaces merging into one. In that sequence, space itself flexes. The curvature changes. The event horizon is not a rigid shell, but a dynamic surface that swells and rings. The gravitational waves we recorded are the space-time equivalent of sound after a bell is struck. So now, when we say that inside the horizon the future is a forced direction, we are not speaking about abstract diagrams alone. We are speaking about regions that actually exist around objects in the sky. Regions from which light has traveled to us in a way that matches, almost eerily, the precise predictions of the theory. Regions whose mergers we have heard. What, then, would it mean to reverse this story? If you take the equations of general relativity in their classical form and simply reverse the direction of time in a black hole solution, you obtain the white hole solution. Instead of matter and radiation falling in from far away and crossing the horizon toward a future singularity, you have matter and radiation emerging from a past singularity, crossing a horizon that nothing from outside can enter, and then dispersing. There is a temptation to treat that reversal like a clever visual trick, a film reel played backward for curiosity. But once Hawking radiation and black hole entropy enter the scene, the question acquires weight, because then you are asking, in effect, can a process that increases entropy in the forward direction, as almost all natural processes do, be realized in reverse? If a black hole is like a piece of music with only a downward beat, steadily losing energy as it radiates over time, a white hole would be like a track played in reverse, only an upward beat. A steady outward rush, as if the universe is returning stored energy in a carefully ordered way. You can almost hear the difference. A black hole's song is a deep, one-way descent. A white hole, if it existed as more than a mathematical twin, would be a pure ascent. In one case, events fall into silence. In the other, they rise out of it. From our usual thermodynamic experience, such ascent sounds wrong. Glasses shatter on the floor and stay broken. Smoke spreads out in a room and does not gather itself into a sharp column and dive back into the cigarette. Heat flows from hot to cold. We rely on this asymmetry so completely that we do not usually see it. It is built into phrases like spoiled milk and spent fuel. The laws underlying those processes, at the microscopic level, are mostly time-symmetric. If you knew the exact position and momentum of every particle, you could run the equations forward or backward, and both would be allowed. The arrow of time we experience comes from the improbability of certain macroscopic states, not from a ban in the equations. The same is true in general relativity. The field equations do not forbid white holes. They support them just as happily as black holes. If you feed in the right boundary conditions, what makes white holes suspect is not the mathematics. It is the extraordinary specialness of the initial conditions they require. Imagine, for a moment, the merger signal LIGO saw. Two black holes spiraling together, radiating gravitational waves. In the forward direction, the waveform has a chirp structure. Frequency and amplitude increase until the merger, then decay as the final black hole rings down. Now, imagine trying to realize the exact time reverse. A black hole in an excited ringing state, somehow absorbing gravitational waves from the universe in such a way that it splits into two smaller black holes that then spiral apart, sending any leftover energy back into the cosmos in a coherent way. The equations would not forbid this, but the universe would have to prepare an unbelievably intricate pattern of incoming waves, tuned to just the right phases and amplitudes, to make it happen. Nothing like that appears in our observations. Nothing in our experience of thermal phenomena suggests that such fine-tuning ever occurs. So when we say that white holes are the time reverse of black holes, we are speaking at the level of solutions to the equations, not at the level of realistic cosmic events. They live comfortably in the space of possibilities, but that space is larger than what the universe seems to choose. This is why, in most modern discussions, white holes are not presented as concrete targets for telescopes. You will not find them on a sky map. No catalog lists confirmed white hole candidates. Instead, they appear as boundary markers in thought, as reminders that our theories, taken strictly, have more room in them than reality seems to occupy. They also act as hooks for something deeper. Once you know that black holes radiate, you cannot help but wonder, what is the end state of evaporation? If a black hole shrinks over immense timescales, does it vanish completely? Does it leave behind a remnant? Does its interior connect to something else? In some speculative scenarios, ideas like black holes tunneling into white holes or black holes giving birth to new expanding regions are explored. In those pictures, a white hole is not a stable fountain sitting in our universe. It is a brief phase in a quantum process, a moment in which a trapped region becomes an expanding one. These are not mainstream, established results. They belong in the realm of hypotheses and models, but they show how the simple time reversal idea can seed more intricate stories. For a late-night listener, it may help to hold a softer image. Think of a black hole as a drum that only ever dampens sound. Hit it, and it rings. But over time, the oscillations decay. Energy is lost as radiation. everything quiets. A white hole would be like a drum that begins in silence and, without being struck, gradually releases a stored pattern of vibrations, louder and louder, until it reaches some peak and then stops. We do not know of any such drum in the cosmos. We do not see unstruck vibrations swelling up in emptiness. But the equations, written on the page, allow you to draw them. So when we say that white holes are not something we can confidently see, we are not being evasive. We are respecting the boundary between what is in the mathematics and what is in the sky. White holes are structures we run into when we push the theory to its most complete, symmetric form. They are part of the logical closure of the map. To visualize that map properly, with all of its regions and horizons and hidden connections, our familiar coordinates are not enough. They stretch and tear in the wrong places. They hide the full shape. What we need is a way to draw an entire space-time, including infinities and horizons, on a single, finite diagram. A kind of cartography that can fold endless distances into a manageable sketch. So, the white hole region, the black hole region, and the outside universe all appear together on one calm sheet. So now imagine that someone places a sheet of paper in front of you and says, "Here, put an entire universe on this, not in symbols, as a picture." When we draw the Earth on a flat page, we already know the trick. You cannot unwrap a sphere without stretching something, so you accept distortions. Continents look larger near the poles. Shapes bend. Mapmakers choose what to preserve. Area, angles, routes. No map is perfect. Each is honest about a different compromise. Space-time is harder. It is not just space. It is space and time together. And yet physicists want a map for it too, not a three-dimensional model, but a simple diagram that shows what can reach what, where light can go, where signals cannot, where horizons lie. To do that on a single sheet, you must compress infinity. Distances that would be endless in reality must fit into a finite width. Events that would be infinitely far in the future must fit somewhere near the top of the page. You are not trying to keep track of kilometers. You are trying to keep track of fate. This is what a Penrose diagram is for. It is a way of drawing a space-time so that light rays always move along lines at 45 degrees, like the diagonals on a grid. It is a way of placing what would usually be infinitely far away at a finite boundary, without losing the essential structure of which events can influence which others. The details of scale are sacrificed. The pattern of possible communication is kept. On such a diagram, a black hole stops being a mysterious dot. It becomes a region, a patch of the diagram from which no 45-degree line can escape to the outer boundary. The event horizon appears as a line slanting at just the right angle. The last possible path light could take outward. The singularity is not drawn as a point in the middle. It is drawn as a kind of edge, a boundary inside the diagram that marks the place where the geometry ends. The first hint that such careful mapping would matter came surprisingly early. After the eclipse expeditions returned, after their plates were measured and remeasured, the results were brought before a wider audience. On the 6th of November 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London, the bending of starlight by the sun was presented as evidence in favor of general relativity. The room, by most accounts, was charged. Headlines later would say that Newton's law had been overturned, that a new view of gravity had been confirmed. The excitement was as much about method as result. The strange idea that space-time could curve had survived its first real astronomical trial. But for most people, including many scientists, this remained a difficult idea to picture. Curved time, distorted distances, light following geodesics in a four-dimensional manifold. Diagrams on flat pages became essential. They offered a way to tame the abstraction. Decades later, filmmakers would reach for the same diagrams in a different language. On the 2nd of April 1968, the film 2001, A Space Odyssey, premiered in Washington, D.C. It would become famous for many reasons, but one of them was the way it treated cosmic scale. Long, quiet shots of spacecraft drifting, a black monolith that seemed to mark some shift in human and perhaps cosmic development. A non-linear ending that felt more like a dream than a plot. The film did not show Penrose diagrams. It did something more oblique. It gave viewers a feeling that the universe could be plotted in more than just orbits and trajectories, that there were regions of experience and meaning that ordinary maps could not capture. It made the idea of a journey through space-time feel strange and haunting. Years later still, another film would bring the specific idea of black hole time to the center of popular imagination. Interstellar premiered at the TCL Chinese Theatre on the 26th of October 2014, and then reached wider audiences in the United States on the 5th of November 2014. For many viewers, this was the first time time dilation near a black hole felt like something lived, not just stated. An hour near a massive object, becoming years elsewhere. A planet's surface experiencing time at a slower rate than a ship farther out. Behind the scenes, physicists like Kip Thorne used tools related to those same diagrams to advise on what could be shown. What orbits might look like, how light would bend, how horizons behave. The public, perhaps without realizing it, grew more comfortable with the idea that time and space could warp in ways that turn everyday intuition inside out. Penrose diagrams live in that same family of aids. They are not photographs. They are not literal pictures. They are distilled maps of causality. If you were to draw a simple Penrose diagram of flat, empty space-time, it would look almost disappointingly neat. The bottom edge would represent the infinite past. The top edge, the infinite future. The left and right sides would represent spatial infinity in two opposite directions. Light rays would travel along lines at 45 degrees, connecting those boundaries. Massive particles would follow lines that tilt more gently, always staying inside the light cones. Nothing obstructs anything. There are no horizons. Every event can, in principle, influence some part of the future outside itself. The diagram is a rectangle filled with evenly spread potential. Now place a Schwarzschild black hole in the center of that universe and extend the solution to its full analytic reach. The simple rectangle is no longer enough. You must carve out a region for the black hole interior. You must draw an event horizon, a null line, at 45 degrees that separates the outside from the inside. You must place a singularity somewhere in the interior, not as a dot in the middle, but as a space-like boundary. In the standard diagram, it appears as a horizontal line above the horizon, tilted so that all future directed paths inside end on it. Suddenly, the map has weather. Outside the horizon, you still see the familiar vertical and diagonal lines. Observers can send and receive signals, fall in or escape, up to a point. Inside, the arrows all point toward the singularity. No path leads back out to the outer boundary. That part of the diagram is like a cave in the map of a mountain, with all trails ending at a single wall. Here comes the twist. When you do not stop at the first quadrant that looks reasonable, when you follow the mathematics to its maximal extension, the diagram does not contain only one such cave. It contains a second, mirrored region in the past. The straight edges of the rectangle become crossed by an X of null lines. At the top of that X sits the black hole singularity. At the bottom sits another singularity that plays the role of a white hole. In this full drawing, there are four main regions. One can be thought of as our universe outside the black hole. Beyond the horizon of that universe lies the black hole interior, ending at the future singularity. On the other side of the X lies another asymptotically flat region, a kind of other exterior universe connected through the central structure. And below, mirrored across a horizontal axis, lies the white hole region, bounded by a past horizon and ending at a past singularity. The Penrose diagram does not tell you that these are separate universes in the science fiction sense. It tells you that, within the idealized mathematics of the eternal Schwarzschild solution, there are multiple regions with different causal relationships. Some cannot send signals to each other. Some are connected only through the bridge of the Einstein-Rosen structure, which itself is too unstable to traverse in any realistic way. The important part, for our story, is that lower wedge, the white hole. In that region, if you draw arrows representing time-like paths, they all point outward from the past singularity toward the future. No arrow crosses inward through the past horizon from the outside regions. If the black hole region is a place where the future ends abruptly at a singularity, the white hole region is a place where the past begins abruptly at one. The horizon there is a boundary you cannot step into from the outside, no matter how you aim your path. You look at the drawing and something quiet happens. You see that the idea of a horizon does not belong only to the future. The past, in this extended solution, has its own horizon as well. A surface across which information can flow in only one direction, out. This is where a Penrose diagram is more than art. It makes the structure of time itself visible in a simple picture. It shows you, at a glance, that the full Schwarzschild spacetime is not just a story about falling. It is also, in its lower half, a story about erupting. It is easy, staring at such a diagram, to slip into talk of parallel universes. The two exterior regions, left and right, look like separate worlds. The white hole region, at the bottom, feels like a different cosmos birthing ours. Films and novels love this kind of imagery. The mathematics is more sober. It tells you that these regions belong to a single, connected spacetime, defined by one set of equations and one solution. They are not alternate realities in the speculative fiction sense. They are parts of the complete geometric structure you get when you refuse to cut off the solution prematurely. Still, even with this discipline, there is room for gentle wonder, because the diagram reveals that general relativity, when treated fully, does not privilege one direction of time in its basic construction. Wherever there is a black hole region with a future horizon and a future singularity, there is, in the idealized, eternal version, a corresponding white hole region with a past horizon and a past singularity. In actual astrophysical settings, we do not expect eternal black holes that have existed forever and will exist forever. They form from collapsing stars. They interact with their surroundings. Their horizons grow, shrink, and distort. The maximally extended Schwarzschild spacetime is an ideal, like a perfect sphere or a frictionless ramp. Nature offers approximations, not exact matches, yet the ideal has a kind of instructive purity. On the Penrose diagram, you can place an observer's world line and see, without solving differential equations, whether that observer can ever see the white hole region, whether signals from there can affect them, whether they can send anything in return. For most world lines in the upper half, the answer is one-sided. The white hole's influence is built into the past, but unreachable as a place. The diagram becomes, in that sense, a map of what can ever matter to you. You trace a line from where you are, or where you imagine yourself to be, and see which parts of the shaded regions fall into your past light cone. The white hole region sits at the bottom, its edge touching the horizons. You cannot travel into it. You cannot mine it or explore it. But if you live in one of the exterior regions of this ideal spacetime, the pattern of light and matter you see might carry the imprint of its existence. For a listener half asleep, you can think of it this way. Someone hands you a drawing made of straight lines and triangles. At first, it looks like a design. Then you notice that some arrows never cross a certain line, that some zones are cut off from others except through narrow openings, that some pieces sit forever in the past. Suddenly, this is not just a design, it is a picture of limitation. You look at a drawing and suddenly see that the past can also have its own horizon. That is where the white hole hides in this story. Not as a glowing object, not as a portal waiting in space, but as a region on a space-time map that lies entirely in the past, sealed off by a horizon that nothing outside can cross. A mark that cannot be touched, only inferred. To understand that region more intimately, we will have to move our attention from the whole diagram back to that lower wedge, and to what it would mean, even hypothetically, for a universe to carry within its history such a one-way fountain, a singularity in the past, a horizon that only lets things out, and a pattern of effects spreading into a future that never quite lets us trace them back to their source. If you keep that lower wedge on the diagram in your mind, there is one more quiet step to take. Stop thinking of singularities only as dead ends somewhere ahead of us, and imagine, just for a moment, what it means to have one sitting silently behind everything instead. We are used to singularities as something in the future of anyone who falls. In the standard black hole story, you cross the horizon, time and space trade roles, and no matter what you do, your world line ends at the singularity. It waits ahead of you the way tomorrow waits ahead of today, a boundary at the far end of your possible experiences. But on the full, eternal Schwarzschild solution, mathematics allows something stranger. It lets the singularity live in the past as well as the future. Not as a mirror image you can visit, but as a kind of starting line, hidden beneath the events you can see. In that lower wedge of the Penrose diagram, there is a past singularity from which time-like paths emerge, cross a horizon, and flow out into the exterior region. That lower wedge is the white hole region. In that region, every path points outward. If you draw the world line of any observer inside, it always runs from the past singularity toward the future, crossing the horizon from inside to outside, never the other way around. No time-like path, no light ray, approaches the white hole from the exterior and crosses in. The horizon there is not a trap for things falling inward. It is a one-way surface for things escaping outward. So we can restate the family rule more cleanly now. A black hole is a region of spacetime from which nothing can escape to infinity. A white hole is a region of spacetime into which nothing can enter from outside. Same family, same general structure of a horizon and a singularity. Two different prohibitions. If you like, you can think of the black hole horizon as a door that locks behind you as you step through, never to be opened from the inside. The white hole horizon is like a door that is permanently locked from the outside. Inside, things can leave. Outside, nothing can get in. This is already strange enough, but the geometry offers more surprises. Inside the eternal Schwarzschild spacetime, the black hole region and the white hole region are connected through a kind of bridge. In the original coordinates, it is hard to see. In the better extended coordinates, it becomes a passage in the diagram linking the two exterior regions through the interior structure. That bridge fascinated Einstein and his collaborator Nathan-Rosen. On the 1st of July 1935, they published a paper exploring the idea that this internal structure could be interpreted as a kind of bridge between two regions of spacetime. We now call it the Einstein-Rosen bridge, one of the earliest appearances of what people would later call a wormhole. In their picture, the two exterior regions in the extended Schwarzschild solution are like two mouths of a tunnel connected in the middle by a throat. At first glance, it is an irresistible idea. A shortcut, a way to go from one universe to another, or from one distant point in the same universe to another, by slipping through a hidden passage inside a black hole. The reality is less accommodating. When you study the Einstein-Rosen bridge more carefully, you find that it is not traversable in any ordinary sense. The throat pinches off too quickly. Any attempt to cross is thwarted by the fact that the bridge collapses before a traveler could make it through. The structure is there in the mathematics, but it is unstable, like a soap film, stretched too far. Still, that image of a bridge connecting otherwise distant regions would not go away. Decades later, ideas about wormholes grew more elaborate. Some theorists would imagine exotic matter that might hold a throat open. Others would link the existence of wormholes to deep questions about quantum information and black hole interiors. In the early 21st century, a provocative idea emerged with a short, memorable label: ER equals EPR. In a paper that appeared on the preprint server RExiv on the 3rd of June 2013, Juan Maldacena and Leonard Susskind suggested a conceptual bridge between Einstein-Rosen wormholes and Einstein-Podolsky-Rosen quantum entanglement. The slogan was simple: perhaps every pair of entangled particles is connected by a kind of microscopic, non-traversable wormhole. The details of that proposal are subtle and technical. It does not turn black holes into science fiction gateways, but it reinforces the sense that the geometry of these eternal solutions, including their white hole pieces, may be telling us something about quantum gravity and the way information is stored and shared. Meanwhile, in everyday culture, time reversal and weird shortcuts became familiar toys. On the 3rd of July 1985, the film Back to the Future was released in the United States. It offered a simple, charming narrative. A car that can travel through time if it moves fast enough and carries the right machinery. Histories can be changed, pasts rewritten, futures repaired. The physics in that story does not resemble general relativity in any rigorous way, but it shows how ready the human imagination is to accept the idea that time might bend, that cause and effect might be negotiable, that paths through spacetime might be more flexible than our daily routines suggest. White holes, on paper, look like the sort of thing such stories would seize upon. And yet, when we step back from diagrams and films, the boundary between beautiful and real becomes important again. The eternal Schwarzschild solution is idealized. It assumes a black hole that has always existed and will always exist, static and unchanging, sitting in an otherwise empty universe. It assumes perfect symmetry, no rotation, no tides from nearby structures, no collapsing star to form the horizon, no accretion disk to feed it. Our universe does not look like that. Stars form and die. Matter falls in. Black holes spin. Collisions happen. Radiation flows. The geometry is dynamic and lumpy. Horizons grow and shrink. Singularities, if they form, do so as the future endpoints of specific histories, not as eternal features etched forever into space-time. In that real, messy cosmos, the white hole region of the eternal solution begins to look less like a literal piece of the world and more like a mathematical footprint, a trace left by the fact that the equations themselves are symmetric in time, even if the actual history of our universe is not. You can compare it to finding the fossilized footprint of some strange animal in rock. The footprint is a real object. It has shape, depth, structure. From it, you can infer something about the creature that left it, its size, its gait, perhaps even how it carried its weight. But whether the species that left the print still roams anywhere, or even ever did beyond that one site, is another question. In the same way, the white hole region in the eternal Schwarzschild spacetime is like a footprint embedded in our theory. It tells us that if spacetime were arranged in a certain symmetric, eternal way, there would necessarily be a past singularity and a horizon that only lets things out. It shows us that the equations remember both time directions. But it does not guarantee that any actual collapse or explosion in our universe followed that pattern. Physicists disagree, quietly, about how much weight to give this footprint. Some see white holes as a curiosity of academic graphing, a byproduct of insisting on maximal extensions and ideal symmetries. Interesting, but not something that nature ever realized. For them, white holes are useful mainly as test cases, as ways to probe the consistency of ideas about horizons and quantum fields. Others treat them as clues. Even if perfectly formed, eternal white holes never existed. The structure of that region might hint at what happens in more realistic scenarios. In some quantum gravity models, processes that look like black hole evaporation or bounce can, for a brief moment, resemble a white hole phase. Information might leak out in ways that echo the one-way outward flow in the diagram. These are not consensus views. They belong on the more speculative side of the map. But they show that white holes are not entirely dismissed. They sit in a soft controversy zone, too delicate and special to be taken as literal predictions, too suggestive to be ignored when we ask what quantum space-time might do at its limits. For a late-night mind, it can help to hold a simple contrasting image. If a black hole is like a starless night, a region from which light does not return, then a white hole is like a dawn with no sunset, only light spilling out, never matched by anything coming in. One is a sky where stars go missing. The other is a horizon where brightness appears without a visible source. In the eternal solution, that dawn is not something you can walk toward. You cannot steer a ship into the white hole region. The past horizon is a door you cannot step through from outside. No matter how powerful your engines, or how cunning your route. The only things inside are those that were, in a sense, always destined to flow outward. The singularity sits behind them in the past, not waiting ahead in the future. If you lived in such a space-time and traced your observations backward, you might find yourself puzzled. You would see streams of matter and radiation emerging from a certain surface. You could never get behind that surface. No probe you send would cross inward. The pattern would hint at a hidden origin, but the origin itself would remain unreachable. In our actual universe, we do not see such patterns. We see jets from active galactic nuclei, powered by accretion disks around black holes. We see supernova remnants, expanding shells of gas from exploded stars. We see the cosmic microwave background, aglow from the hot early universe. All of these have histories we can model, sources we can, at least in principle, understand. None of them behaves like a true white hole, endlessly ejecting material while absolutely refusing entry from outside, anchored to a past singularity. That absence is telling. It suggests that if white holes play any role in our universe, it is not as visible, long-lived objects sitting on the sky. It is more probable that they live at the edges of our understanding instead, in diagrams, in equations, in speculative models about how singularities might be resolved by quantum gravity. When you look again at the Penrose diagram, with its crossed null lines and shaded wedges, the white hole region feels almost calm. It sits there at the bottom, feeding into the rest of the diagram. A dawn that has already happened. You cannot visit it. You can only acknowledge that, in the eternal story the equations tell, the past is structured with as much care as the future. Whether nature ever followed that particular script is a separate matter. Our telescopes and detectors, for now, speak mostly of black holes. Their birth in collapse, their growth by accretion and merger, their slow whisper of Hawking radiation in theory. White holes, if they exist at all beyond the page, are silent. So the question becomes softer, almost like something you might turn over just before sleep. If the equations allow these one-way fountains, and yet the sky shows us none, what is that telling us about the way our universe chose its initial conditions, about the direction of time it prefers, about the quiet bias built into its history? And if the answer is that we will almost certainly never point a telescope at a patch of sky and say there is a white hole, then the mystery shifts. It moves from "where are they?" to "why were they left off the stage?" leaving us with a different kind of wonder as we listen to the darkness between the stars. There are mysteries that do not hide at the edge of distance, but at the edge of when. They are not beyond our reach because they are too far away in space, but because they sit in a direction of time we have no road into. White holes belong to that kind of hiding place. If you think back to the Penrose diagram, to that lower wedge that represents the white hole region in the eternal Schwarzschild spacetime, you can feel why. The white hole's singularity, in that picture, sits entirely in the past of everything that flows out from it. Its horizon is a surface that light can cross only in the outward direction. Nothing from the outside ever falls in. All the arrows inside point up and away. Mathematically, some of the light rays that reach the exterior region from the white hole come from what is called past infinity. In the eternal solution, the white hole belongs to a past that stretches forever downward on the diagram. It is not an event that happens at some particular time and then stops. It is part of a space-time that has always been there. That already makes it hard to connect to the universe we actually observe. Our cosmos has a beginning in a hot, dense state. It expands, it cools, structures form. Black holes are born when massive stars collapse or when dense regions in galactic centers gather enough mass. They carry, each of them, a kind of birth date, a when. In the eternal solution, there is no such birth date. The black hole and the white hole regions are features of the spacetime for all times. The symmetry between them relies on that eternity. As soon as you say, "This black hole formed from a star on a certain day," you have broken the perfect mirror. There is no longer an infinitely extended past region that could host a white hole twin. So the first big reason we do not see white holes is simple and subtle. In the pure, eternal solution, light from the white hole region is tied to an infinite past. Our real universe does not offer that infinite past. It has a beginning of its own. Whatever white hole structure the mathematics allows is pushed behind that beginning into a part of the diagram that our cosmos never realized. The second reason is even more down to earth. Real black holes are not platonic objects sitting in vacuum. They stack histories. A massive star exhausts its nuclear fuel. Its core collapses. The outer layers explode. A remnant remains, which may become a black hole. Gas falls in. Magnetic fields twist. Accretion disks shine. Nearby stars feel the pull. Every one of these steps is a departure from the eternal, syrup-smooth spacetime of the Schwarzschild ideal. The geometry is dynamic, lopsided, noisy. Radiation flows outward. Matter speckles the surrounding. Trying to fit a perfect white hole into that tangled narrative is like trying to find a complete, untouched reflection in a broken mirror. Even so, our instruments have become powerful enough that if long-lived white holes existed in any simple way, we might hope to spot some signature. Instead, each advance reveals more black hole behavior, more ordinary explosions, more subtle flows of gas, but nothing that looks like a region that endlessly emits while never accepting anything in. On the 24th of April 1990, the Hubble Space Telescope was carried into orbit aboard the shuttle mission known as STS-31 and released to begin its work. In NASA's logs, the precise moment of deployment is recorded, down to the minute and second, as if to mark that instant when our eyes moved beyond the blur of the atmosphere. From then on, Hubble has given us views of galaxies, nebulae, and distant clusters that stretch our sense of depth. You can look at a Hubble image of a rich galaxy cluster and feel, for a moment, that you are seeing almost everything. Spirals, ellipticals, faint smudges, arcs of light from gravitational lensing. Yet even with that reach, even with decades of observation, nothing in those fields insists on being interpreted as a white hole. The light carries histories of mergers, collisions, starbursts, but not an endless one-way outward fountain tied to a past singularity. Then came an even deeper eye. On the 11th of July 2022, NASA released the first full-color image from the James Webb Space Telescope. The so-called first deep field. It showed a tiny patch of sky, smaller than a grain of sand held at arm's length, containing thousands of galaxies at a range of distances and ages. Some of the light in that image began its journey when the universe was very young. For many people, it felt like looking almost straight into the beginning. The next day, on the 12th of July 2022, at 10:30 in the morning on the east coast of the United States, a larger set of Webb images was formally revealed. That specific announcement time, written into press releases and schedules, has already become part of the story people tell about how we saw farther and farther back. Not just the data, but the moment when the data became a shared human experience. Hubble and Webb together show us that we can, in a very real sense, look both far away and far back. The deeper the image, the more ancient the light. And yet, even in these glimpses of the early cosmos, we do not see anything that demands the label white hole. What we see instead is a universe that began hot and dense almost everywhere at once, then expanded and cooled, forming structures gradually. White holes, in their pure form, are not like a new planet we might have simply missed because it is faint. They are not like a gas cloud hiding behind dust. They are expressions of a very particular direction of causality. They require that the past be set up in a way that is, from our thermodynamic standpoint, extraordinarily special. An everyday analogy might help settle this. Imagine you are in a quiet room and you hear a phone ring. You look around. You see a phone on the table. A moment later, someone presses a button to answer. You may not know who is calling or why, but the sequence feels natural. First, someone presses a button to call. Then, somewhere else, The phone rings. Now flip the order. Imagine hearing the phone ring, but knowing for certain that no one has yet pressed call anywhere in the universe. No finger has moved. No signal has been sent. The ringing has no past. It is as if the sound has simply appeared, with the cause sitting somehow in the future instead. That kind of story is what a white hole asks you to accept at the level of space-time. An effect, a flow of light and matter, whose cause is tucked into a singularity in the past that cannot be reached or examined, and which cannot be fed from outside. The moment you try to map that onto a realistic universe with a finite beginning and with everyday thermodynamics, the story starts to fray. So, when we say that we do not see white holes, it is not because we lack big enough telescopes. It is because the very specific conditions white holes require seem not to fit the way our universe actually unfolded. The absence is, in a sense, a positive clue. It tells us that the cosmos we inhabit chose a simpler, less finely tuned path. That absence does not make white holes meaningless. If anything, it sharpens their role. They become markers of where our intuition about time and cause reaches its limit. They are like shapes in the space of possibilities that our world passed near but did not occupy. When we use Hubble to measure the light curves of supernovae, when we use Webb to study the atmospheres of exoplanets, when we listen with LIGO and Virgo for the merging of black holes and neutron stars, we are exploring a universe that takes the arrow of time seriously. Things collapse. They merge. They radiate. They cool. Rarely, if ever, do we see large-scale phenomena that look like time-reversed versions of these processes. Even the rare, exotic events we do see, like jets from active galactic nuclei or fast radio bursts, can be traced to mechanisms that fit into this forward-leaning story. Energy is released from something that was previously storing it. There is a before. There is an after. The before has lower entropy locally. The after has higher. The direction is constant. In that sense, white holes serve as a kind of mirror we hold up to our theories. By studying why they do not appear, we learn something about the kinds of initial conditions our universe likely had, and about the strength of the thermodynamic arrow that runs through everything from boiling water to star formation. So if you go outside on a clear night and look up, the fact that you will not find a white hole is not a failure of our instruments. It is a quiet reaffirmation of something deeper, that the time we live in flows one way, that causes and effects line up in a way that lets fragile beings like us make sense of the past and guess at the future. We can still keep the picture in mind. The lower wedge on the Penrose diagram, the white hole region, feeding into the rest of the space-time, its past singularity forever hidden, its horizon forever one way. We can still use it as a reminder that the equations know how to run backward even when the world does not. And slowly, that leads us toward the largest constraint of all. Not the reach of telescopes, not the sensitivity of detectors. The thing that truly limits the reality of white holes is not distance or faintness. It is the way entropy behaves, the way order tends to decay, the way broken cups stay broken, the way every natural process we know seems to favor one side of time over the other. The horizon that hides white holes from us most effectively is not drawn in space. It is drawn in that one direction we can never turn around and walk the other way. The horizon that matters most here is not at the edge of a black shape in the sky. It is the one you feel in your bones, when you notice that some things break and never unbreak. Take a glass on a table. You can drop it. It shatters. Pieces scatter across the floor. If you wait long enough, you might sweep them up and throw them away. What you will not see, no matter how long you stare at the tiles, is the reverse. Each shard hopping back into the air at just the right moment, turning and sliding neatly into place. The cracks sealing, the glass landing upright in your hand. That missing scene is what we call entropy in disguise. Everyday life is full of these one-way moves. Cream mixes into coffee and does not separate itself back out. Smoke spreads through a room and does not gather itself back into a tight column to sink into the cigarette. Ice cubes melt in warm water and do not spontaneously reappear as perfect cubes in a now colder glass. There is a direction hidden in all of this. not the direction you face, the direction of time. What makes the story strange is that the most fundamental equations we use to describe matter and forces do not, by themselves, prefer one direction. If you took a film of atoms bouncing off each other and showed it to a physicist who could see only the positions and momenta, they might not be able to tell whether you were playing it forward or backward. The laws that govern those microscopic motions are, in almost every case, time-symmetric. Einstein's field equations for gravity are like that too. If a certain arrangement of space-time curvature and matter is allowed, then the time-reversed arrangement is also allowed. If a black hole that forms and persists into the future is a valid solution, then a white hole that erupts from a singularity in the past and fades is also valid. So, at the level of equations, white holes feel right. They are as legitimate as black holes. The mathematics accepts them with no complaint. Our lived world does not. In the 19th century, long before black holes and white holes were given their names, physicists were struggling with this mismatch. The steam engines of industry made it obvious that some processes were irreversible. You could let heat flow from a hot reservoir to a cold one and extract useful work. You could not, without doing additional work, make heat flow from cold to hot and reload the reservoir. There was some quantity that always seemed to increase when left to itself. In the year 1865, Rudolf Clausius gave that quantity a name: entropy. He framed it in the language of energy and temperature, building what we now call the second law of thermodynamics. In his description, the entropy of an isolated system never decreases. It can stay the same in ideal reversible processes that are more thought experiment than reality. In anything messy and real, it goes up. Entropy gave time a direction in a way mechanics had not. You could now say, without referring to human memory or perception, which way the film was running. The direction in which entropy increases is what we call forward. A few years later, in the year 1872, Ludwig Boltzmann tried to push the idea deeper. He wanted to derive this one-way behavior from the time-symmetric motions of atoms and molecules. His H-theorem, as it came to be called, attempted to show that, under reasonable assumptions about how particles collide and scatter, a quantity related to entropy would tend to move in a preferred direction. It was an audacious move. It said, in effect, that the arrow of time might not be an extra law added on top, but a statistical consequence of how incredibly many microscopic configurations correspond to what we, at a larger scale, call disorder, compared to order. Is Prisation. They will reason side. Boltzmann's work sparked debates that outlived him. Critics pointed out that if the underlying equations were reversible, one could just as well run his logic backward. Others raised paradoxes about rare fluctuations. To this day, the interpretation of entropy and the arrow of time is a deep, subtle topic. Still, a broad lesson emerged. The reason we do not see glasses unshatter is not that the equations forbid it. It is that the specific microscopic state corresponding to shards on the floor is unimaginably more probable than the microscopic state corresponding to perfect glass, hovering with just the right momentum to land on the table. There are far more ways for the world to look messy than to look tidy. Now bring this back to space-time. A black hole, in its simplest description, is what you get when matter collapses inward and crosses a point of no return. The process is, at a coarse level, an increase of entropy. Matter that once had structure and complexity falls into a region described by a handful of parameters: mass, charge, spin. Whatever detailed information the matter carried seems to be lost behind the horizon. Hawking's work shows that black holes themselves have entropy proportional to the area of their horizons, and a temperature, and that they radiate in a way consistent with thermodynamics. So, in the story of black holes, the arrow of time points along the collapse. Things fall in. Entropy goes up. The horizon area, in classical general relativity, never decreases. It is the gravitational version of cream mixing into coffee. A white hole is the formal time reverse of this story. Instead of matter with rich internal structure collapsing into a smaller, simpler region, You have matter and radiation streaming out of a horizon in an exquisitely coordinated way, as if they had been prepared by some hidden mechanism in the past singularity. The horizon area shrinks as the eruption proceeds. Entropy, at least in a naive reading, seems to flow the other way. In other words, at the level of coarse description, a white hole looks like a massive entropy decrease. You can picture it the way you picture that glass. The black hole is the act of dropping it, watching it shatter, sweeping the pieces into a whole. The white hole is the fantasy reverse. The pieces leap out of the hole, rise into the air, assemble neatly into a glass, and land in your hand, leaving the floor spotless. Thermodynamics does not have a line saying this is absolutely banned. It has something more patient, and in a sense, more ruthless. It says that such a thing is allowed by the microphysics, but so astronomically improbable that, for any practical universe made of many interacting parts, you can safely treat it as never happening. One way to visualize this is to imagine the universe as a slope. Entropy is the steepness of that slope. Low entropy states sit high up. High entropy states sit low down. A black hole forming from a collapsing star is like a ball rolling downhill. It may bounce, wobble, and spin, but the general motion is downward toward more probable configurations. A white hole is like a ball that sits deep in the valley, and then, without any push, spontaneously rolls uphill in just the right way to end up perched at a precise point at the top. The laws do not forbid the uphill roll. They simply give it a weight so tiny that, when you average over all possible histories, it vanishes into insignificance. This is what people mean when they say white holes are impossible in a physical sense. Not impossible by decree, impossible by statistics. The arrow of time we feel in our muscles and habits is this statistical tilt made visible. You wake up older, not younger. You remember yesterday, not tomorrow. Heat leaks through walls in winter. Batteries run down. Galaxies use up their gas in star formation. Everywhere you look, processes favor one direction. General relativity, left to itself, does not care. It will happily host a spacetime in which this tilt is reversed. But as soon as you populate that spacetime with matter that obeys ordinary thermodynamic behavior, the reversal demands fantastically special initial conditions. Every particle must start in just the right place, with just the right motion, to play the film backward. In the context of black holes and white holes, this tension becomes sharp at the horizon. The horizon is where the global structure of spacetime and the local behavior of fields meet. We can draw Penrose diagrams and talk about past and future singularities. We can also talk about what a detector hovering near the horizon would actually measure. In the early 21st century, as people tried to reconcile black hole evaporation with quantum mechanics, a new puzzle appeared. On the 13th of July 2012, a preprint was posted to the Arxiv by Almheri, Marolf, Polchinski, and Sully. It argued in rough terms that three things many physicists wanted to keep could not all be true at once. That information is not lost in black hole evaporation. That physics near the horizon looks like ordinary empty space to a freely falling observer. And that quantum field theory works in the usual way outside. The tension became known as the firewall paradox. One way out suggested that the horizon is not the smooth, innocuous boundary classical general relativity describes, but a place where something violent happens to infalling observers. A firewall of high-energy excitations. The details of that debate are technical and ongoing. What matters for our quiet journey is what it reveals. Even today, we do not fully understand what a horizon really is when quantum effects are included. We know that black holes radiate. We know that their entropy scales with area. We suspect that the interior and the exterior are entangled in subtle ways. But the precise story of how information winds through that structure is not finished. White holes sit at the extreme of this uncertainty. They represent the most aggressive way to ask the question, what if time ran the other way here? Not just in the geometry, but in the bookkeeping of information and entropy. They are like thought experiments turned into exact solutions. Precisely because they are almost impossible, they become the most fascinating places to ask, What if? A devil's surfertango. What if there were a region in space-time where the arrow of time, as experienced by matter and fields, pointed outward from a singularity, rather than inward toward one? What if, for a brief moment, or in a special context, the ball really did roll uphill? Not forever, but long enough to leave a mark on the rest of the universe. You do not need to believe that such a region exists in our cosmos to appreciate the usefulness of the question. By thinking about it, you probe the seams in our understanding of time. You test how robust the second law really is when gravity and quantum mechanics are both strong. In the deepest quiet, you can think of the universe itself as a kind of gentle machinery that amplifies small asymmetries into large arrows. A slight imbalance in initial conditions leads to a huge contrast between what is typical in one time direction and what is typical in the other. The glass on the floor, the smoke in the air, the stars in the sky, all confirm that contrast. Against that background, a white hole is like the faint outline of a path the universe almost certainly did not take. A road up the slope that is drawn in the equations but left untraveled in reality. The quieter it is, the clearer you hear that arrow moving, not as a sound, but as a pattern, in how memories form, in how heat spreads, in how black holes grow and slowly evaporate. The forward pull is everywhere. Still, the mind can step gently to the side and ask, in a whisper, if the universe ever did, even once, create something that behaved like a white hole, even for a fleeting moment, how would it appear to us? Would it be a long-lived object, glowing steadily? Or would it be a brief event, a kind of space-time flare, a sudden uphill roll that cannot last? If it happened at all, it would probably not sit patiently on the sky like a new kind of star. It would pass through the universe more like a gesture than an object. So imagine, carefully and slowly, not a long-lived white hole sitting at the center of a galaxy, but an event, a moment of eruption, a brief phase in the life of space-time itself when, for reasons buried in conditions we may never fully see, the usual downhill flow of entropy hesitates and, just for an instant, seems to flutter. To get even that far in imagination, the universe has to deal itself a very special hand. In ordinary stories, a black hole forms when matter collapses under its own gravity. There are many ways to start that collapse. A star can exhaust its fuel. A dense cloud can gather more mass than pressure can support. The initial state does not need to be tuned with ridiculous precision. A wide range of messy beginnings can lead to the same kind of dark end. A white hole is the opposite. For the equations to produce a region where matter and radiation stream outward through a horizon that nothing can enter, the state on that horizon and behind it in the past has to be almost impossibly specific. Tiny deviations, small disturbances, generic fluctuations would ruin the pattern, either preventing the white hole from forming or making it collapse immediately into something else. The more honestly we think about entropy, the more extreme this requirement becomes. You would need the early universe, or some local pocket of it, to be arranged so carefully that the subsequent evolution looks like the time reverse of a collapse. Every particle, every quantum of radiation, would have to begin in just the right state, so that later they appear to erupt outward in a coherent way from a region that never accepts anything in. At first glance, that level of tuning makes talk of white holes feel like fantasy. But once black holes themselves are understood as thermal objects with a temperature and a spectrum of radiation, the idea of reversal gains a more serious foothold. The story is still extremely hard, it is still pushed to the very edges of plausibility, but it is no longer sheer poetry. In the 1970s, Hawking's work on black hole radiation turned these questions from speculation into calculation. In his detailed paper on particle creation by black holes, received by the journal on April 12, 1975, he laid out how quantum fields in curved spacetime lead, in a precise way, to the emission of particles from the vicinity of the horizon. The spectrum has the form of thermal radiation. The black hole behaves as if it has a temperature inversely proportional to its mass. That temperature is tiny for astrophysical black holes. A black hole, the mass of a star, would have a temperature much lower than the cosmic microwave background. It would absorb more radiation from space than it emits. Only black holes, much smaller than any we have evidence for, would evaporate quickly. Even so, the principle is clear. The gravitational field near the horizon can convert vacuum fluctuations into real particles. Pairs are separated. One falls in, the other escapes. From far away, it looks as though the black hole is losing energy. If, in the forward time direction, a black hole radiates and slowly shrinks, then in the mathematical time reverse, a white hole would absorb that same pattern of radiation and grow. At this level of abstraction, the logic is clean. The trick is to understand whether anything like that could be realized in a universe where entropy almost always climbs. As physicists tried to reconcile Hawking radiation with the idea that information is not lost, the horizon itself came under scrutiny. The firewall paradox, first posted as a preprint on July 13, 2012, suggested that the benign, empty nature of the horizon in classical general relativity might not survive quantum scrutiny. Maybe, the authors argued, there is a kind of high-energy barrier there after all, if certain cherished principles are to be saved. A year later, on June 3, 2013, another provocative idea arrived in the form of the ER equals EPR proposal. It suggested that entangled particles might be connected by microscopic wormholes, and that the interior of a black hole could be understood, at least in part, as a web of such connections. The slogan did not magically turn black holes into safe gateways, but it reinforced the sense that the inside and outside of a horizon are woven together in ways that go beyond our classical pictures. In this tangle of ideas, white holes appear as one more test structure. If the interior of a black hole can be thought of as a place where information is stored in entanglement, then a process in which that interior transitions into an outward flowing phase, a kind of quantum bounce, is not completely absurd in some models. It might resemble, for a very short time, a white hole. Here, controlled imagination matters. Instead of picturing a white hole as a calm, luminous object existing for millions of years, like a star that only ever shines and never absorbs, it may be more realistic to imagine a sudden change in the state of spacetime, a bounce moment, a transition in which a region that was trapped becomes, under quantum rules, untrapped, and expels energy and information in a brief burst. A public-friendly image might be this: if a black hole is a fist, clenching shut, squeezing everything into a tiny region, then a white hole, in this event-like sense, is a hand snapping open, not slowly relaxing, snapping, fingers springing outward. Whatever was held inside is suddenly free. That snap, if it happens, does not look peaceful. In many descriptions, white hole, like configurations, are unstable. Any small perturbation from outside, any stray particle or ripple, can disrupt the delicate balance and either prevent the white hole from forming or force it to collapse back into an ordinary black hole. The moment you place such a region in a realistic environment full of radiation and matter, the time-reversed pattern struggles to survive. This is why, in the more cautious literature, one reads about white hole bounces not as static objects, but as transitions with finite duration. They are like brief, dramatic phases rather than fixed residents of the cosmos. They may happen, in some scenarios, near the end of black hole evaporation, when quantum gravity effects become dominant. Or they may be used as mathematical models of how singularities could be resolved without true infinities. Either way, they are not the sort of thing a telescope would track calmly over centuries. They would flicker through history, leaving traces rather than portraits. So how would you look for such a thing, if you wanted to? The first step is to let go of the idea of a white hole as a point on a sky map and think instead in terms of signatures. A sudden pulse of energy with an unusual profile, a pattern in gravitational waves that does not match any known merger or collapse. A causal structure in a simulation where information seems to emerge from a region that no world line in the model ever enters. Physicists already use this sort of reasoning. When they search for exotic phenomena, they often begin not with "where is it?" but with "what trace would it leave if it existed?" Would it distort the cosmic microwave background? Would it produce bursts of neutrinos? Would it alter the distribution of high-energy cosmic rays? Much of this work stays far from the public eye, living in charts and bounds rather than in headlines. White hole events, if they play any role at all, would be among the most elusive targets. Their parameter space is narrow, their lifetimes are short. Their signals, if any, might overlap with more mundane phenomena. A gamma ray burst from a collapsing massive star, for example, is already a kind of space-time eruption. Disentangling one speculative process from another would be difficult. It may be that the only lasting role of white holes is not observational but conceptual. They serve as stress tests. You take your theory of quantum gravity, your model of information flow, your favorite resolution of the firewall paradox, and you ask, if I run this story backward, does it make sense? Does it allow a white hole-like phase? If so, under what conditions? If not, why not? In this way, white holes do not need to exist as events to do useful work. They act as questions written in the margins of our theories. Still, for the sake of sleep, you can sketch a gentle scenario. Imagine a black hole that has lived a long time, swallowing matter, ringing with mergers, slowly radiating. Its horizon has shrunk to a size where quantum effects in the geometry itself are strong. The classical picture of a singularity and a smooth horizon is no longer reliable. Inside, quantum gravity does something we do not yet know how to calculate in full. Instead of a sharp end, suppose the interior region undergoes a transition. The trapped surfaces disappear. The geometry reconfigures in such a way that what was once an inward path becomes an outward one. For a brief interval, perhaps shorter than any human scale, there is a phase in which degrees of freedom that were effectively locked away become able to influence the outside again. From far away, this might look like a sudden burst of radiation, a last, intense flicker as the black hole completes its evaporation. From the inside, if that phrase even makes sense in such a context, it would resemble a bounce, a shift from toward the singularity to away from it. Calling that phase a white hole is, in some sense, a stretch. It would not match the eternal, clean white hole region of the Schwarzschild diagram. It would be more like a cousin, a momentary inversion of the usual arrow inside a tiny domain of spacetime. And yet, the language has power. It lets us connect an abstract, almost mythic idea, a region where nothing can enter, and everything inside must leave with concrete questions about how gravity and quantum mechanics coexist. It gives a name to one possible way the universe might avoid true singularities, not by erasing the strange regions, but by letting them evolve into something else. A moment, a breath, a fountain, then gone. By the time any such event could happen for a stellar mass black hole, the universe would be unimaginably old and dilute. Stars would long since have burned out. Galaxies would be dim. Whatever witnesses existed would not be like us. Perhaps no witnesses at all. The event would be, in that sense, almost private. So when we speak, tonight, about white holes, as bounces and snaps and fleeting fountains, we are not planning observations. We are feeling out the edges of possibility. We are asking how far the time symmetry of our equations can be trusted in a world where glasses shatter and do not reassemble. The irresistible comparison, of course, is with the one event we do believe really happened on a cosmic scale. The beginning of expansion itself, a hot, dense state everywhere at once, out of which light and matter streamed. If a white hole is a local, idealized fountain of space-time, then the Big Bang is the one thing that, in mood if not in detail, feels similar. It is tempting to say they are the same. That somewhere, behind our observable universe, there is a black hole whose interior looks like our cosmos, and that our beginning was its white hole end. Tempting. And in need of careful, patient, unpicking. So we turn, almost inevitably, to the one eruption we are sure about, the one outpouring that left traces everywhere we look, even in the dark, between galaxies. If a white hole is defined, in the simplest way, as a region where everything moves outward and nothing ever falls in, then the early universe is the closest thing we have to a lived example of that mood. In its first moments, the cosmos was hot, dense, and rapidly expanding. Light and matter streamed out from a state so extreme that our best theories still hesitate when they approach it. We call that history the Big Bang. Not a sound, not an explosion in pre-existing space, but a pattern of expansion and cooling. The further back we trace our models, the hotter and denser the universe becomes. Until, at some finite time in the past, the description reaches a kind of boundary, not a place, a moment beyond which the equations cannot be naively extended. In that sense, the Big Bang feels like a past horizon. You cannot simply go back before it in the usual way. Our standard cosmological models do not describe an earlier, cooler universe collapsing into that state, the way a star collapses into a black hole. They describe that hot, dense phase as the earliest frame in the film that our current theories can reliably project. This is the first, easy similarity with a white hole. Both are past boundaries in a story of outward flow. Both feel like beginnings that you cannot enter from earlier times. It is also exactly where misunderstanding starts, if we are not careful. In popular images, the Big Bang is often drawn as a bright point in an otherwise black void, with galaxies flying away from it like debris from a bomb. That picture is intuitively appealing and almost entirely wrong. The Big Bang is not a point in space that you could fly toward if you aimed your rocket carefully. It is a moment that happened everywhere in space at once. If you roll the cosmic film backward, every galaxy you see around you does not move towards some remote central location. The distance between any pair of distant galaxies shrinks. Space itself contracts. The entire observable universe, in the early times, was compressed into a smaller volume. There is no privileged center in those equations. Every place is, in a sense, as central as every other. A true white hole, in the textbook sense, is more local. It is a region with a horizon and a singularity tied together in a relatively compact structure. Matter and light emerge from it, cross the horizon, and flow into the surrounding space. You can draw a boundary between inside and outside. You can imagine, at least in principle, navigating around it. The Big Bang does not fit that shape. There is no outside region where someone could watch our universe erupt from a point. There is no external horizon around the whole thing in the way there is around a black hole. The universe is not expanding into something else. It is expanding in the sense that distances between unbound objects increase with time. Remember that first Webb deep field? On the 11th of July 2022, when NASA released that grain of sand-sized patch filled with thousands of galaxies, many people described a feeling of almost touching the beginning. The light from some of those galaxies left when the universe was young. Their images arrive now as fossils of early times. The next day, on the 12th of July 2022, at 10:30 in the morning, on the east coast of the United States, the full first set of Webb images was unveiled. For a brief window, it felt as though technology had turned the cosmic clock backward. Not by changing time, but by letting us see further down its slope, closer to that hot, dense phase, when everything we now know was compressed into a smaller, rougher universe. A few months before, on the 12th of May 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A star, the black hole at the center of our galaxy, a soft ring of radio light around a dark interior, an anchor in the middle of the Milky Way, marking an end state for massive stars and gas clouds. In that same year, humanity held in its mind both extremes, a central black hole that swallows, and a sky full of faint, ancient galaxies, whispering about a beginning that poured energy outward. Putting those two together, it is tempting to draw a line. A white hole at the start, black holes at the ends. The universe as a single long breath, a contraction into some pre-Big Bang state, then a sudden outward surge, then, over aeons, the formation and evaporation of black holes as the last exhales. As an image, it is soothing. It makes the story feel closed. It turns the raw mystery of why is there something rather than nothing into something like, The universe breathes, a gentle cycle, a rhythm, a universe that feels less like a machine and more like a living thing. The danger is that this comfort can slide into overclaim. From the standpoint of cosmology, we do not have observational evidence that the Big Bang is literally a white hole of some larger spacetime. Our measurements of the cosmic microwave background, of the abundance of light elements, of galaxy distributions, all support the idea that our universe, on large scales, has evolved from a hot, dense early phase. They do not tell us what, if anything, that phase came out of. They have a best of a slave mast. Some theoretical models do imagine a prior contracting universe that bounces into our expansion. Others imagine black holes in some parent universe giving birth to baby universes inside, with the inner beginning looking, from our perspective, like a Big Bang. These ideas are intriguing. They make clever use of the white hole notion. They offer ways to link microscopic physics, black hole thermodynamics, and cosmology, but for now, they live mostly in the realm of possibility, not of established fact. So it may be more honest, and still calming, to treat Big Bang as white hole, as an intuitive metaphor. It captures a certain feel, that our beginning is an outflow, not an inflow, that it marks a past limit, the way a white hole singularity does in the eternal solution, that you cannot send a probe into before the bang, any more than you can steer a ship into the white hole region from outside. The metaphor helps us talk about causality direction. It reminds us that, for us, the deepest past we can meaningfully discuss is already a high entropy, expanding state compared to whatever truly fundamental description might exist. It hints that asking what caused the Big Bang may be a different kind of question than asking what caused a star to explode. Where the metaphor breaks, the reality becomes more interesting. The Big Bang is not a point in an existing space. It is the beginning of the kind of space and time we inhabit. It involves quantum fields, curved spacetime, and perhaps ingredients we have not yet discovered. A white hole, in contrast, is defined within a pre-existing spacetime as a specific region with a horizon. It does not create the geometry around it. It lives inside it. When people say, maybe the Big Bang was a white hole, they often mean something softer. Perhaps our observable universe is the interior of some larger structure, connected through a kind of one-way boundary to a realm we cannot see. That does not contradict any current observation, because we cannot observe beyond our horizon anyway. It also does not follow from them. Treating the Big Bang as white hole, like in mood, rather than in strict identity, lets us keep the best parts of the comparison. The sense of outpouring, the recognition of a past boundary, the idea that the earliest moments are not ordinary times but something like a phase change in the fabric of reality. At the same time, it keeps us from claiming more than we know. We can say, the equations of general relativity, extended and combined with quantum hints, certainly allow for stories in which black holes give birth to new expanding regions. We can say, some models of bouncing cosmologies resemble, in their diagrams, a white hole opening into a new branch of spacetime. We cannot, yet, point at our particular universe and state with confidence that this is how it began. If you let that uncertainty be gentle instead of frustrating, something soft appears. We live in a cosmos whose origin, in the deepest sense, is still open. Our best tools can trace it back to a fraction of a second after the earliest moment. Our telescopes can collect light that has been traveling for billions of years. Our equations can describe, with surprising accuracy, how a hot plasma cooled, how atoms formed, how structure grew, but at the base of all that, there is still a quiet question. Did the story start there? Or is that start simply the place where our current theories run out of breath? If the Big Bang resembles a white hole in its outpouring, the inverse question appears naturally beside it. If our beginning feels like a fountain, could the ends of massive objects, the black holes we now image and listen to, resemble the beginnings of somewhere else? Could every black hole, in some larger picture, be the seed of a separate expanding region? invisible to us, in which some other observers, someday, look back and see their own version of a Big Bang. We do not know. Many cosmologists would say that without a way to test such ideas, they remain more like philosophy than physics. Others would reply that today's philosophy sometimes seeds tomorrow's testable theory. For us, lying in the dark under a sky full of old light, the value may be simpler. It gives us permission to imagine an even larger map, one in which our universe, with its beginning and its black holes and its eventual quiet, is a patch, not the whole. One in which the white hole is not an object to find, but a pattern that can appear in different guises, in diagrams, in cosmic births, in speculative baby universes. That mood opens the final door in this journey, because once you allow yourself to entertain, carefully, the possibility of Big Bang elsewhere, the mind drifts naturally toward the most magnetic fog in this landscape: wormholes, branching universes, and the question of whether a fall into a black hole is always an ending, or could, in some stories, be the start of something new on the other side. So imagine, for a moment, that the inside of a black hole is not only a cul-de-sac, not only an end wall painted black. Imagine it as a hallway, narrow, curved, lit only by the falling things themselves. You step into it, and as you walk, the hallway quietly shortens ahead of you. The floor collapses toward your feet. No matter how fast you try to run, the far door moves closer, faster. You are not just walking toward the end. The end is folding itself around you. This is what makes people ask, is there really nothing beyond that wall? Or is there more structure hiding in the mathematics, just out of reach? When Einstein and others first looked at the extended Schwarzschild solution, they noticed something that did not quite fit the simple dead-end picture. There was that bridge, the Einstein-Rosen throat, linking two exterior regions through the interior structure. In the abstract coordinates, it looked like a tunnel between otherwise separate universes. If you drew it with a pencil on paper, it resembled an hourglass or a narrow neck between two bulges. On the 1st of July 1935, Einstein and Nathan-Rosen published their paper describing this construction. They did not call it a wormhole. That word would come later, from other mouths. They were trying to understand whether one could interpret certain exact solutions as describing particles or connections in spacetime. Still, the image stuck. Two regions, one neck, a bridge. If you think of spacetime as a kind of flexible fabric, the Einstein-Rosen bridge is like a sketch of that fabric, pinched together so that two distant patches touch. It is beautiful in the way a geometric drawing can be beautiful. Simple, symmetric, complete. And, like a drawing, it is fragile. In the clean Schwarzschild case, the bridge pinches off too fast to cross. By the time anything tries to move through, the hallway has already collapsed into the singularity. Later work would show this more clearly. Unless you add exotic ingredients, negative energy densities, or other departures from everyday physics, wormholes that connect distant regions and stay open long enough to traverse are not stable. The pencil bridge is there in the solution, but the universe does not seem inclined to build it in full. Even so, the idea of wormholes took on a life of its own. The American Physical Society published a historical article called The Birth of Wormholes on the 25th of March, 2005, tracing how this concept moved from rarefied relativity discussions into broader scientific culture. By then, wormholes were not just technical structures in equations. They were familiar motifs in novels, television shows, games, and of course, cinema did its part. Interstellar, which premiered at the TCL Chinese Theatre on the 26th of October 2014, put a wormhole right at the center of its story. A smooth, shimmering sphere near Saturn, a gateway to another part of the universe. People watched characters fly through it in a matter of minutes. For many, that was the first time the word wormhole carried not just a definition but a set of images, sounds, feelings, The film took artistic liberties, as it had to. The original Einstein-Rosen bridge is not something you can use as convenient transit. Realistic wormhole solutions, if they exist at all, require ingredients we have never seen in nature at macroscopic scales. The point, for us, is softer. Once you start seeing black holes not only as endpoints, but as parts of larger geometries, it becomes hard not to wonder what might lie beyond, even if that beyond is only in the space of possibilities. One such possibility is that the hallway which ends at a singularity in classical general relativity might, under quantum rules, bend around into somewhere else. Some speculative models suggest that, instead of a true singularity, there could be a bounce. The collapsing region might give birth to a new expanding region on the other side of the gravitational choke point. From the perspective of that new region, the beginning would look like a white hole, an outpouring from a boundary no one could cross from outside. These are sometimes called baby universes. The phrase is intentionally soft. It does not tell you how big they are, how long they last, whether they are connected in any useful way to the parent universe. It simply captures the idea that space-time itself might branch, that what we call inside the black hole could, in some deeper story, be the seed of a fresh cosmos with its own arrow of time. This is not something we have observational access to. You cannot stand outside and watch a bubble universe bud off the interior of a black hole the way you can watch a soap bubble detach from a ring. The horizons involved, if the picture is even roughly correct, hide such processes from our view. That is why these ideas live near the boundary between physics and philosophy. They satisfy the equations in certain frameworks. They may even solve some puzzles about entropy and information, but for now, they do so behind a veil. At the same time, they join hands with the white hole idea in a gentle way. From the parent universe's point of view, a black hole is a region where everything goes in. From the child universe's point of view, if it exists, the same structure would look like a white hole, a past boundary from which everything flows out. One throat, two stories, depending on which side you inhabit. You do not have to believe in baby universes to appreciate what this does to your sense of scale. It suggests that our usual words, inside, outside, beginning, end, may be too small. That, what looks like an ending from one vantage can look like a beginning from another. That causality itself may have more elaborate patterns than the ones we meet in daily life. And here, slowly, the soothing part returns. Because even if no wormhole has ever been traversed, even if no baby universe has ever budded off, even if every black hole in our universe is truly an end for matter that crosses its horizon, the structures that general relativity and quantum theory allow are still there in the background. They show us that the universe could, in principle, host configurations where time reverses in certain regions, where information finds odd pathways, where horizons play double roles. A white hole, then, may not exist as a neat dot in a catalogue. It may never grace a telescope image or a press release. Instead, it exists as a question you can hold without needing an answer. Can time, anywhere, ever, reverse its usual arrow? Can causality, in some hidden corridor of space-time, take a back door that our senses never glimpse? Those questions do not demand conclusions. They do not insist that you pick a side or memorize a model. They simply invite you to sit with the possibility that reality is larger, stranger, and in some ways more generous than the slice we inhabit. For sleep, that can be enough. You do not need to solve the firewall paradox before morning. You do not need to decide whether baby universes are real, whether wormholes can exist, whether the Big Bang was a white hole from somewhere else. You can let those ideas drift past like slow satellites in your thoughts. Notice them, acknowledge their shapes, and let them recede. What remains underneath is a quieter kind of comfort. The comfort of knowing that the universe, at its most serious, does not owe us simplicity. It offers us consistency, symmetry, patterns. It also offers us regions of uncertainty where different stories are still allowed. In those regions, meaning is not given. It is made by beings who can wonder. Tonight, as you lie under whatever portion of sky is yours, You can imagine a place where everything can only leave, not to run away, not to escape responsibility. Just to illustrate, in the language of geometry, that not all doors are symmetrical. Some are built for entering, some are built for exiting. Some, like horizons, are drawn by the curvature of spacetime itself. Somewhere in the space of possible universes, there may be clean white holes, eternal fountains in perfectly symmetric diagrams. Somewhere in the space of theories, there may be a final, quiet understanding of how black holes handle information, how time and entropy entwine, how the inside and outside of horizons really speak to each other. We are not there yet. That is all right. You can close your eyes with a single, light question in your mind. Not a heavy one about purpose or fate. Something smaller and gentler, like, if I could watch the universe from outside its time, what patterns would I see that I cannot see from here? Would white holes stand out as bright knots in that fabric? Or would they be rare, delicate threads, almost never woven? You do not need to answer. Let the question soften at the edges. Let it blur, the way galaxies blur when you take off your glasses and look up. Let it become less a problem to solve and more a feeling that reality is deep, that not knowing is allowed, that being small in such a vast structure is not a failure but a kind of honesty. And if, somewhere in your sleep, your mind drifts back to that hallway inside a black hole, or that fountain that only ever flows outward, let it. You can watch them from a safe distance, knowing that they are, for now, shapes in our best theories. Shapes that bend your intuition just enough to make room for awe. When the next day comes, the questions will still be there if you want them. For now, you can let them dim with the room, like a screen going dark, until all that is left is the quiet fact that you live in a universe where such questions make sense to ask.